Something else we can do. We can take a look at precipitation. Precipitation is the opposite of dissolution, the opposite of dissolving. It's what happens when a solid comes back into being from its solvated ions. What we can use equilibrium for is we can predict whether something is going to precipitate or dissolve based on the equilibrium position. We're going to use the concept of Q again. Okay, remember Q is the reaction quotient or ion product quotient. It's calculated the same way as K, except the concentrations don't necessarily have to be at equilibrium. And then we can use the value of Q, the size of Q, to compare to K to figure out whether or not we're at equilibrium or if we need a shift. Okay, so Q is just like KSP, QSP you might want to call it, but it's not at equilibrium position. And remember that if Q is greater than K, that tells you that more reactant is going to form. Reactants in the case of solubility are solids. And so if your more reactant is going to form, that means you're going to have precipitation until you reach equilibrium again. If Q is less than K, that means more products need to form. And in the case of solubility, products are the ions. So more of the solid will dissolve to get back to equilibrium. So here we have, we're going to mix 750 milliliters of cerium nitrate, and the concentration is given, and 300 milliliters of cerium iodate, and 300 milliliters of KiO3, potassium iodate. We want to know if cerium iodate will precipitate. Okay, so we're going to calculate Q value and compare it to K. The K value is on the chart in your book. So cerium iodate will dissolve into cerium 3+ and 3 iodate ions. Okay, that's the solubility that we're working with here to see if it's going to precipitate or not. We're going to see what Q is and compare it to the K value. Okay, Q is calculated the same way as K, so concentration of cerium ions, concentration of iodate ions cubed. We have the concentrations given. Okay, we have to figure out based on the total volume, which is 750 and 300. So we have to find the moles of each solid ion and then divide by the total volume. So the 750 milliliters times its concentration of the cerium nitrate divided by the new total volume, which is 1050, and then multiply that by the 300 milliliters of the cerium of the KiO3 multiplied by its concentration divided by the new total volume, and then we cube that. And we get 5.32 times 10 to the minus 10th. The KSP value for cerium iodate is 1.9 times 10 to the minus 10th. 5.32 times 10 to the minus 10th is greater. When Q is greater than K, we produce more reactants, and the reactants in this case are the CeIO3. So if we're producing more solid, we're going to precipitate. So yes, given this situation, when I mix them, we will precipitate some cerium iodate. Try this one. Solution is made by mixing 150 milliliters of 1.00 times 10 to the minus 2 molar magnesium nitrate and 250 milliliters of 1.00 times 10 to the minus 1 molar sodium fluoride. Find the concentration of magnesium ion and fluoride at equilibrium with solid MgF2. So in other words, it's saying at equilibrium, what are your concentrations of the two ions that would make the precipitate MgF2? KSP is 6.4 times 10 to the minus 9th. So there's your equilibrium expression. We need to figure out whether the concentrations are high enough to cause precipitation, just like we did in the last example. So we find Q and compare it to K. Q for magnesium fluoride is Mg2+ times fluoride ion squared. The 150 milliliters times its concentration divided by the new volume. The 250 milliliters times its concentration divided by the new volume squared for fluoride. We got 1.46 times 10 to the minus 5th. Q is greater than K, so it will precipitate. So that's our first half of our problem. Now what we want to do is figure out, well, all of it, is all of it going to precipitate or only some of it? Well, not all of it is going to precipitate. Okay, we need to figure out how much is going to precipitate out. There will be some ions left in solution, so not all of the magnesium and fluoride are going to get together to form this compound. We want to figure out how much is left. Okay, so we're going to use stoichiometry to figure out how much of the salt is created based on how much of reactants we put together. And then we're going to take that amount and we're going to create an ice chart to figure out how much is going to be left at equilibrium. Okay, so 2 steps, 3 steps really. The first step was figuring out whether or not we're going to get a precipitate in the first place. So it's sort of like an acid-base problem that we've done before, okay, in that we had multiple steps where we had to use stoichiometry and then equilibrium concepts to get at our answer. All right, so first let's figure out how much of it goes to completion. We started with 1.50 millimoles. Remember, molarity times volume equals the number of moles. Well, if volume is in milliliters, then you get millimoles instead. So we have 1.50 millimoles of the magnesium ion. We have 25 millimoles of fluoride ion. We don't care how much of the MgF2 we're producing here. What we're interested in is how much of this is going to actually combine. Okay. Well, clearly the magnesium is the limiting reactant, so all of that is going to go away, and only 1.50 millimoles of the 25 is going to go away for the fluoride. Okay, but remember that its stoichiometry is 1 to 2, so it's actually 3 millimoles because it's got to be multiplied by 2, and 2 times 1.50 millimoles are going to be produced. Okay, so some of it dissolved. Now we want to know how much is left in solution. So our MgF2 is the salt, and that's producing Mg plus 2 and F minus. We have no magnesium in solution because we used it all up in the top chart there. We used it all up to create this magnesium fluoride. So we don't have any, when the magnesium fluoride is going to then dissolve, we don't have any magnesium ion to start with. But we do have a little bit of the fluoride ion, 22 millimoles divided by the total volume of 400 milliliters. Some of the magnesium fluoride dissolves, minus X. Some produces some magnesium ion, plus X, and twice as much fluoride ion, plus 2X. So at equilibrium, our expressions are X for the magnesium ion concentration and 5.5 times 10 to the minus 2 plus 2X for the fluoride ion concentration. Plug that into our KSP expression for magnesium fluoride as Mg concentration and F minus concentration squared. The KSP value is 6.4 times 10 to the minus 9th, which we could look up or was given in the problem. X times 5.5 times 10 to the minus 2 plus 2X, all squared. X is 2.1 times 10 to the minus 6th. So the concentration of magnesium is 2.1 times 10 to the minus 6th molar. The concentration of fluoride is 5.5 times 10 to the minus 2 minus 2.1 times 10 to the minus 6th times 2, which is very small and won't affect the 5.5 times 10 to the minus 2. So our fluoride ion concentration doesn't really change, and it stays the same. We can use the concept of solubility equilibrium for something called qualitative analysis. And qualitative analysis, qualitative meaning we're not so much concerned with numbers here, but just the process of doing something with these solutions. And essentially what we're going to do is we're going to separate a solution that contains different ions using the differences in their solubilities. Okay, we do this by precipitation. So we have a solution that it contains 1.0 times 10 to the minus 4th molar copper ions and 2.0 times 10 to the minus 3rd ion lead ions. We're going to add iodide ion to that solution slowly. And we want to know which is going to precipitate out first, the copper iodide or the lead 2 iodide. Neither of them are very soluble. Which one is less soluble? Because the one that's less soluble will come out first, right? So we can calculate the concentration of I minus ion, right? We know how much lead ion is in there. It's given in the problem. We know the KSP value. We can look it up for lead 2 iodide. And we can calculate the concentration of iodide needed to just start precipitating lead 2 iodide. Right when you're at equilibrium, you're just about ready to precipitate. Okay? So if you have a greater concentration than 2.6 times 10 to the minus 3rd molar of iodide, you're going to start precipitating lead 2 iodide because that's the minimum concentration needed for equilibrium. Any more than that, you precipitate out the salt. You start shifting your equilibrium back to the left. Okay. For copper iodide, we do the same things. The KSP for copper iodide is 5.3 times 10 to the minus 12th. Cu plus times I minus concentration. We already know the Cu plus concentration from the problem. So we calculate the I minus concentration is 5.3 times 10 to the minus 8th molar. So any greater than 5.3 times 10 to the minus 8th molar will start to precipitate CuI. Well, it takes much less iodide to precipitate copper iodide than it does to precipitate the lead 2 iodide, because it takes, 2.6 times 10 to the minus 3. You're talking, 5 powers of 10 more concentrated to precipitate the lead. So the much lower concentration of iodide required to precipitate the CuI means the CuI is going to come out first. Okay? This is like a little flow chart that you can use for qualitative analysis to figure out how to separate. So we have a solution of silver and mercury 1 and lead 2 ions. If we add cold HCl, we're going to precipitate out the chlorides. Okay? If we precipitate out the chlorides, we'll get silver chloride, we'll get mercury 1 chloride, and we'll get lead 2 chloride. If we heat that solution, the lead 2 chloride will dissolve, and we'll get lead ions. We can precipitate the lead ions out with chromate ion later. Okay, but we can take the mixture of silver chloride and mercury 1 chloride, which they don't dissolve at high temperatures, and we can add aqueous ammonia. When we do that, we create a complex ion with the silver. It's silver with 2 ammonia molecules near it, and that's going to dissolve. But mercury, the mercury solid, will stay precipitate. You can filter that out. Then you can precipitate out the silver as silver chloride and filter that out. You can precipitate out the lead as lead chromate and filter that out. So this is just like a flow chart of how you would separate those 3 ions out of solution by varying solubilities and varying temperatures to create a situation where you precipitate out 1 ion at a time and then filter it out of the solution.